All right. Levels are good. And here we are. Boop, boop, boop. Okay, yeah. Hi, welcome back. I'm Agent Ultra, and on this stream, I like to code little projects, programming projects with you, and for you, and in front of you, and all kinds of things. I do it mostly in the programming language Haskell. And, yeah, just because I like it. It's fun. And because, like, nobody believes me that you can actually write real software, so... I'm not a researcher. I'm a smooth-brained hacker who's just grew up in the times and used to do all kinds of languages. I've been in the industry for a frighteningly long time, and yeah, I write stuff in Haskell these days. So happy to share with you this week, and for the last few weeks we've been learning about wave function collapse. I've been learning a lot by doing this project, and we're going to continue on with that tonight. So welcome back. It's nice to see you. We're going to go over into my directory, get my editor up and running, and get our code building. No, we're going to run the test runner in the fast mode with the file watcher. There we go, that's how we're going to do that. Boop. And that's going to resize a little bit. What it likes to do. Okay, cool. There we go. Code. Come here. So last week there was a slight mistake that I quickly fixed after the stream was over. Not a big one, kind of a big one, but small thing was just possible patterns. Let's make sure I actually got the most recent code here. Anyways, one of these was supposed to be... Oh yeah, no, possible patterns. Originally we had the possible patterns as just the full set of array pattern indices, but we actually needed just the ones that are set to true. The patterns that are left in here, in this cell. So just added that small little thing. Okay, and okay. There's still plenty to do, but we're getting into... yeah, remove possibility, remove pattern. We're getting into propagation, and we're getting close to propagation in our algorithm here. So, one thing I kind of went a little bit further ahead on than was we went to collapsing, but we still have to choose a cell with the lowest entropy across the whole wave in order to get things started. And of course we have to remove possibilities, so add another to-do item, choose cell with lowest entropy. Okay, cool. All right, so let's remove possibility. I think we could probably do that one. Collapse, let's add it here, say, closer to the other cell functions. I'll call it remove pattern. Maybe we could do possibility makes sense. Pattern index, probably. From the cell, we get a new cell back with that pattern index removed. Now, this is the function where when we remove a pattern index from a cell, we cached the cell total weight and the cell sum of weight log weight in the cell data. And that's where we have to like recalculate those after removing this pattern index from that cell. That's the two steps we've got to do, recalculate the total weight. and sum of weight, log weight. Alright, so we got the pattern index here. We can call pattern X maybe, and the cell. Pattern match out the record wildcards. My general rule of thumb actually with record wildcards is not to use them when the same type is on the left side of an arrow and the return type is here, and then this is like the matching return type here. Found that in prior projects we've done on the stream that was kind of a bit of a pain in the butt because it overloads the names here. Like it shadows the names of the record functions that get generated. And so if you want to use record constructor syntax, it gets in the way. So we'll just use cell here. And that's okay because we got overloaded record dots, so not a big problem there. Okay, so all possibilities is an array. We just have to set this particular index to false, which we know how to do. So let's return a cell. I'm going to pick that equal sign and put it over here. Cell possibilities. If the cell collapsed, we might have to check for that here. Cell total weight, we'd have to do that. And cell sum of weight, log weight. Okay, so cell possibilities, that's going to be cell.cell possibilities. With array.update syntax here, array.update. And that takes a list of association lists. Yeah, we're going to give it the pattern index, the pattern X, and set it to false. We might not even actually... That one we might actually be able to do with just the plain array set operator, actually. Instead of this array update syntax thing function. Blah, blah. We have value, bounds, indices, elements, sucks, incremental updates. Oh, right. This isn't a mutable array, so we're not going to do that. But you can do mutable. You can do mutable arrays in Haskell. We just haven't in this implementation yet. We're trying to keep things straightforward and simple so that we learn, and so we can write some good tests and have like an implementation we trust, so that we can write the more impure, mutatey one and kind of test that it's correct against this one. That's okay. That works. Cell collapsed. For removing this one, it could be that this cell gets collapsed. It could be the last remaining cell in the cell possibilities. Do we have is collapsed, or did I write that already? Cell collapsed. It collapsed. Is it true that it is? Okay. We'll need. I think we might need a function for that. Maybe collapsed. Or check for collapsed. And we need cell. We need this. So let's bind that. Remaining equal. that. Let's back up here. Okay. So then we need check collapsed remaining. And that could be remaining. And then we need a cell total weight. We have total weight. Total weight. Oh, we need the frequency hints in order to calculate that. Alright, total weight. Remaining possibilities and hints. And then some of like what weight log weight. Remaining possibilities and hints. All right, check collapsed. We just have to implement this. What do we have? The array, pattern index, the bool, and we want to return maybe pattern index. This one's going to be interesting. This one's going to be a little bit... And that's because of existence. Or... Well, yeah, a kind of existence. So, if we go through this and all of the bools are false here, right, it's not collapsed. It is beyond collapsed. Right, we shouldn't be able to get to that point, but we may need to know about that here. And if there's one element that's true, that means it's collapsed. Otherwise, it's not. So there's like there's actually three returns, possible return values here. Well, we kind of, like, the type kind of forces us. Yeah. Or we have... Yeah, we should probably do it with a type rather than a runtime error. Just because if we want to be able to go back and implement, say, backtracking, it might be useful to know that this has happened just so that we can implement that. Or we can ignore it and just say we only care about the two cases. It's going to kind of make our code here a little bit... But we can deal with that. Not string, really. We need a better error for that. Okay, so what we want to do is take all of the elements and we want to check if at least if all are yeah, let's see, we need all are false, we need at least one, and we need otherwise. I'm going to, what do we say? I guess we could have a function here. Call it exactly one of array.elms. We have exactly none. Then we return left. No patterns. No remaining patterns. And then we have exactly one. Return. Gotta return the pattern index. So this will have to return its index. And then exactly more. Oh no, we need to return maybe pattern index. So we need just. And this will be right nothing. Kind of weird, right? Okay, so we need this helper function exactly one that returns this type, the values of this type. I'll put it down here. We have exactly none. We have exactly one. I'll probably make this a little bit general. Exactly many, or exactly more, I can't remember. Fish brain, what's going on? Yeah, exactly more. Okay. Make it A like that, that. Okay, and then we have an array of X type to A, and we return what is it? Exactly once. Exactly one. I'll cross the array elms there. I should probably just pass the array. Yeah, so that we can do this. Array XA to exactly once result X. Or exactly one. And just to make sure, I don't think data.list has It has all, and yeah, functions like that. Any, has any and all, I think. And or any, all. Yeah, which isn't going to be quite right. Okay, so there we go there. So in order to tell if we have exactly one, we have to know that we have to look at all the elements. We could sort them and just take the first one. Maybe. Well, not the super greatest, but we could do that. Yeah, might be okay. Alright, so first we take the LM. No, because we need the index of the one. Yeah. So we do have to traverse it linearly. Okay, so I'm going to need to carry around some state, if I found it or not, and the array elements. Go is going to be maybe X. And we have the list of... that's not going to work really either because of reasons. Let's do a fold. Yeah, let's do this as a fold. We get our function here. We'll start with exactly none. As our accumulating state over the array's association list. Okay, so this one needs to be exactly one result x, xa, exactly one result. Yeah. So we'll call this function find element, exactly element. We'll call it exactly. And then we have exactly one result of x here. That'll work, I think. Okay, so that's our accumulator and our index. We don't actually care about the... Well, we do care about the value. Okay. So in the case where the accumulator is exactly none, I don't think and this is true, then we can set it to exactly 1. And then we need the index. Call it I, maybe. Oh, we don't, the reason why we're getting this type error is because we don't actually specify what type A is, and so we can't say it's a Boolean here. So we need a function that takes an A to a Boolean. V such that f of v what's this one? Okay, it doesn't know that my A's here is the same A here is the same A here. I think, well, it should have scope type variables, right? I think V is an A3. What is it? No. I'm just trying to remember which one it is. Overview. I want the overview. I just want the list. There we go. Oh, what was it called? Deriving, no, not deriving. Type. Data type contexts. No. I thought that was. I think I'm thinking of scope type variables, and this should be thing. So maybe I'm wrong about this. I just write it without that. You're happy with that? Okay, you can infer it. Fine. Okay, so we don't have all the pattern matches. These are all pattern matching errors. That's good. So exactly none. If we have we have a v, and our function fv, and we have exactly 1. We go to exactly 1. If we have exactly none, and we have some I FB and not f of v. And we still have exactly none. We have exactly 1. IV such that f of v, then we know we have exactly many, or exactly more. And if we have exactly 1, IV not FV, then we still have exactly 1. I guess it doesn't matter. Let's find that E, and then we have the same E. And then if we have exactly more, we always have exactly more. That doesn't change. Cool. Then we probably need to go back up here. Let's give it ID. And that'll solve that. And then we just need to give... yeah. Since returns either string may be pattern index because of the error that could possibly happen. Which means we're going to have to propagate that error up to remove possibility. And do here, we can get collapsed, maybe collapsed, and check collapsed, giving in the remaining array. And then we can put that here, maybe collapsed. Turn. Okay, and then oh, exactly 1. We just need a constraint here. Ooh, I'll fix that. Not exhaustive. We're missing a couple. Exactly none, and an exactly 1. I think in this case, for exactly 1, we have FB, then we switch to exactly 1. Otherwise, we're just the same. And then we're missing... oh, that covers them all? Okay. Perfect. Just pop that over into the old REPL. Probably just write a couple of tests for this. We do array, we do list array, that's right. 0 to 0. Or we'll do 0 to 1. We'll do 0 to 2. If this has false, 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 we should get exactly none. That's right. And if the middle one is true, we should get exactly 1 of 1. Yeah. And the last one is true. We should get exactly 1 of 2. We do. Yeah. I think we're good. And if we have true here and true here, we should get exactly more. Yeah. Super. And I think that it finishes the implementation of a remove possibility. Alright, we take out the possibility of this particular pattern index, collapse, check if it's collapsed, possibly, and then return the cell with the remaining, maybe collapsed, we reach calculate, yeah, okay, it's all good. Okay, lowest entropy. Okay, the lowest entropy one is going to be fun. Let me pull up my pen so I can draw. It's pretty easy to explain, but the basic idea is that when we go to select the next cell we want to collapse in the algorithm, we use the entropy calculation that we built out, that function, in order to determine the cell's entropy value. And we have to get the next lowest one as part of the algorithm. In constraint solving problems, this is called like the observation step. In case you want to go learn more about this stuff on your own, which I highly recommend. All right, so we're going to observe the cell with the lowest entropy, and we're going to collapse that one. And the whole reason, as I understand it, as we learned a while ago when implementing the entropy stuff, is that we want to have this function will help us pick a cell that is hopefully the least likely to lead to contradictions, where we get to this place where we have a cell that has exactly none for some reason when we go to remove a possibility from it or something. A cell that can't be collapsed, which would be bad. So when we go to collapse a cell, say this one here, all right, we collapse it down to one possibility, and then we have to propagate out the results of that choice to the neighboring cells. All right, so we're gonna using the adjacency rules. We're gonna go to this cell, and we're gonna remove all the ones that we're gonna leave only the ones that could be adjacent to this one. Right. Same here. We're going to go to this cell, and we're going to remove all the ones that aren't allowed to be adjacent to this one. Or in other words, leave the ones that can be adjacent to the one we collapsed. In all 4 directions. Now, by removing those, we may end up having to propagate out more. Right, and this will spread out across the wave. As we remove possibilities from each of these cells, calling our function remove possibility, we recalculate those weights, right, and that changes the cell's entropy. And so the next, after we've done this collapse step, we go to observe again, and we check for the next lowest entropy. Well, which one is it going to be after this has run its course, right? And we go to pick another one. It's going to be this one here. It's going to be this one up here. It's going to be this one down here. It's going to be this one down here. It's going to be one of the other ones that have been, like, you know, spread out from the wave. I'm thinking that we should keep a list of the lowest entropy cells, so that the lowest entropy cell is always at or close to the top. Right. And that way we don't have to go searching for it every time. Every time we go to collapse a cell and remove it. Yeah, we can add it. That's pattern. We're going to add that cell to our heap. That's basically, I'm going to go with a MinHeap here, I'm thinking. That way we can pop off the MinHeap, and then we have the lowest entropy cell always there. And then we don't have to go searching for it. At the cost of updating the heap, but I think that'll be lower than searching these. Because we can imagine this grid's going to get quite large. And we don't want to be searching tens of thousands or hundreds of thousands of cells in every pass inside the loop. Because it's going to be in a loop, right? Skaboosh, skaboosh. Makes sense? I think so. And if we go back to our kind of like sketch. Right. So while they're on collapsed cells, so we're going to be doing this choosing quite a bit. So I think it'll behoove us to keep a list of the lowest entropy cells in a MinHeap. And so choosing will just be popping off on that MinHeap. Fortunately, we don't have to go and implement MinHeaps, I don't think, though. There will probably be one on Hackage. Heap. There we go. Heaps. Haskell implementation of minimum, maximum, minimum priority, maximum priority on custom ordered heaps. Cool. We just need the minimum one, I think. Let's add it to our package. Oh, I mean, like other signals if you're looking for libraries, by the way. I've done this a few times on stream, but there's some pretty good signals if your library is well maintained and stuff. This is probably fine. Although the copyright could be updated. Maybe heaped libraries don't need to be updated once they're done, as long as it works on the newer compilers. It's all good. Oh, that's not the home page. Anyway, I'm sure it's fine. If it's not, we'll find a different library. Add it here, heap. Okay, just building it. Looks like it's compiling. Let's take a peek. Data.heap. MinHeap. Okay. Out of here, import data.heap, MinHeap, import data.heap, qualified as. Oh, sorry. Sorry, the code base I work on at work uses the post qualified, but like by default it's pre-qualified before the module name. Oh. And sometimes I always get twisted on that. Okay. Alright, so then we need a function to get a cell out of our heap. The choose next function. I think we'll add this to the state. Cell entropy list. This will be a heap, a MinHeap of cell. I guess that's all we need, right? Yep, just one type parameter, A, okay. So then, there's our query functions, empty, singleton, insert. Okay, so we give the item, the heap, and the item. Okay. So is that default when I insert a cell into the heap? Does that mean I get to give... Like, how's it picking the min? Is it ord? Yeah, I think it's probably using the ord instance of our value. Which isn't quite going to work for cell. Well, we have to give an ord instance for cell, I guess. I would have to give like a pretty custom instance for that, because we want it to be keyed by the entropy of the cell. This function. I guess maybe we have to use our own... Or we give the tuple with load cell. We'll order by the first element, maybe? We can create a new type for that to hang the instance off, the ord instance off for this. That way we don't have to add a funky ord instance to cell directly. think that might be the way to go. So let's do that. Where do we want to add it? New type. Keep cell. Entropy cell. Float. Cell. And then I'll add my usual standard deriving EQ and show here. Instance, ord, entropy cell. Entropy. Don't actually care about the cell. Oh wait, just entropy cell. There. Like this, where. Haven't actually implemented ord in a while. I forget what it's supposed to be. Let's just get it to go there. Go info ord. And that info command will just tell you things about the type class. Alright, so we have compare. The minimal we have to implement is compare or less than equal. So instance ord of entropy cell. Where? Entropy cell X or something. Compare entropy cell Y is X compare Y. Cool. Oh, I got some unused variable warnings. Yeah, okay, let's clean those up. More non-exhaustive. Good, gotta catch those. You know what? I'm gonna fix those in a separate step. Leave those for now, just so I don't get my code mixed up. Okay, so we have that now. The entropy cell, and the ord on entropy cell is on its first element, so now we should be able to enter entropy cells into our heap list and pop those off. So then we can get a function in here to get the next, choose the next cell with the lowest entropy. I'll put that down here. Choose cell. That's going to be a state of our wave state, returning a cell. I'll leave that undefined at the moment. Compile everything. I will get rid of that for now. I know I'm going to use it, but I'm just going to get it to go away so I can make a commit here. Cool, 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 cool. Work in progress, add, choose, sell. And then I'm going to clean up these warnings. And exactly 1. Okay, so in this case here with exactly 1, we have exactly 1, and the current value we're looking at is exactly 1. In this case, it doesn't matter. So we can just do this. Yeah. Right, and that gets rid of those warnings. Just putting it up there. Boop, 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 boop. Okay, back to where we were. Choosing a cell. So we go to choose a cell. We're going to pop off the heap to get the lowest entropy one, and as long as it's not already collapsed, we can choose that one. So let's get our heap entropy cells. Waste entropy cells. Oh, entropy list. Wave state entropy list. Bad naming. Good catch, me. Okay. So we have our entropy cells there. Okay, so we're gonna pop off the cell. That's where I'm going to need this. And we got view. It returns a maybe item with the remaining heap. Okay. So we have to put that back in the state. I might want a helper function for that. heap.view, entropy cells. Oh, that's a maybe. Right? Yeah. So let's pattern match on that instead of let binding it. Okay, now we have nothing or just the cell and the remaining entropy cells. In the nothing case, we have a problem here. We shouldn't be able to get here. Add a little comment to fix that later. So this case here would be basically a contradiction. I think. Or we should just not be able to get here, period. Yeah, we shouldn't be able to get here, period, because if we have fully collapsed the wave, this won't be empty. Right? And if we have reached a contradiction, it also shouldn't be empty. So maybe we need to handle that. I'll put a to-do there to handle that. So I'll look at that at some point more closely. For now, though, we get the cell, and we have the remaining entropy cells. So here we have to interrogate the cell. If it's not collapsed, or if it's collapsed or not, basically. If we have that, it's collapsed cell. Collapsed, just collapsed. Oh, it's entropy cell, right? So let's deconstruct that here. Entropy cell. We don't actually care about the entropy, just the cell. There we go. Thank you, GHC. Okay, so then, what do we got to do? We have to, if it is a collapsed cell, then we need to choose the next one. We need to try again. So we're gonna put we're gonna put the remaining cells back in here in the state with modify strict and that's where wave state cell entropy list is equal to remaining entropy cells. Okay. So then if the cell is collapsed, we want to choose a different cell. Let's choose the next one. Otherwise, if it's not collapsed, we can use this one. We know it's the minimum one. Least entropy, so we can return it. Okay, now let's see. There's one case we're missing here, and that is when we have a group of cells at the top of the heap that have all the same value. Remember, the OR instance tells us less than or equal to, so they could be all equal. Among those cells, which one should we choose? All right. We could just choose the one off the top of the list, maybe? Or we could choose randomly. If we want, I think we could do randomly. And we could do randomly if... Let me reorder this here. In entropy cell, we add a little bit of randomness to this float value for each value that we enter into the heap when we enter the entropy cell. Maybe we could have a little function for that. What do we call it? Like add entropy list, add cell, add cell, add entropy cell. Add entropy cell. No, this isn't, by the way, I should also be honest. We're working from this gridbugs implementation, and this idea of using the heap is clever, and adding the minimum, adding the randomness to it, I think is probably, yeah, it comes from here. So choosing the minimum entropy cell, I think is a good idea. So rather than iterating over the cells each time, choose the minimum. Yeah. All right, and then I got the idea by reading this to do the randomness thing. So you add a little bit of randomness to each of the cells, and that way they add it here. I don't think we need to. We can do it a slightly different way, but that way they're all random when they get inserted into the heap only, though. Right, we're not adding it to the actual entropy in the formula there. So yeah, just wanted to make sure that clear that that I was kind of crimping that from here. So I thought that was cool. But yeah, the general gist of using MinHeaps for if you're in a loop and you need to keep things in order, definitely. Add entropy cell. So we're going to do that with cell in state, wave state. Okay, so we go here, we get the heap. Entropy cells. We get the wave state cell entropy list. And we're going to need the random generator. So we have actually rand between int, but we want a rand float. We'll go to wave state float. Wave state generator. X and the gen prime, the next state of the generator. We'll use uniform R. I think that'll be fine. With low being 0, float, and high being 1. Generator. And then we modify and return. Right. Call it random. I'll call it random noise. It might be a better algorithm for this. I'm just going to use this for now. Hopefully that'll be between some random float between 0 and 1. Like pure random noise. Well, there's different algorithms of generating different distributions of noise and stuff, but I think this will be pretty close to white noise, maybe. Hopefully it'll just be good enough. Yeah, so noise, random noise. And then we want to add the entropy cell, the entropy cell to the cells. Entropy cells prime equals heap insert, heap item. So that's gonna be entropy. Okay, heap. Okay, no problem. So we'll go entropy cell. And then we'll add noise plus the entropy of the cell and the cell to insert entropy cells. Pull that over to the left a little bit. And a little too much. Okay, and then we can insert that in for the state. Wave state entropy cell list, or cell entropy list. And that'll be entropy cells. Cool. Alright, so that adds a little bit of noise to the entropy cell when we go to add it into the heap. So that is, oh, and then we calculate the entropy of the cell while it's in there. We add a little bit of noise to it so we know it's always random, so that if there are any elements, we know the elements at the top of the list won't be exactly even, like whatever one we pick off will be the one we pick. We go to choose a cell. Cool. Alright, let's commit that right there. Add finish choose cell. Add entropy cell. Oh, I kind of doubled up the work on this one. Oh well. Okay. So then, what do we gotta do? I think that covers choosing the cell. So I think that means we can move on to collapsing. Got that. So yeah, I guess we can move on to propagation at this point now. I think we've got that, yeah. We did that, yeah. Yeah, I think we just have to move on to propagation. So this is where we need to do that thing that I was talking about now. Let's clean the commits we have so far, and then we'll start looking at that. Yeah, rebase interactively. Move this one up. Squash that and that one. Reword that one. Squash that one and that one. Boom. Choose cell and add entropy cell. Okay, so let's learn about propagation. Okay, so propagation enforces the adjacency rules by eliminating choices of tiles from cells. Okay. If we propagate after every cell is collapsed, no matter which cell or possible tiles for the cell, in our case patterns, are chosen, the resulting output of the core algorithm will always respect the adjacency rules. Okay. Each time a tile is chosen for a cell, it's likely that there will be fewer choices of tile available for the surrounding cells. This is because of the output. The output must satisfy the adjacency rules. When a choice of tiles locked in, the adjacency rules tell us which tiles may be chosen for the cells surrounding the locked in cell. So, it's kind of as I was explaining earlier. Looking beyond the immediate neighbors. So in addition to updating the possibilities of cells adjacent to the collapsed one, we can often remove some tile choices from cells further away. The key idea which we will rely on is this. If it's possible to place a tile in a cell, then in each of that cell's 4 immediate neighbors, it must be possible to place a compatible tile according to the adjacency rules. I like that. That's a good formulation. Formulating by like an invariant. I think we could probably even turn that into a test. for our implementation. Somehow. So this is more applicable to propagation if we consider the contrapositive of this statement. For a given cell and tile, if any of that cell's immediate neighbors... Alright, for a given cell and tile pattern, if any of that cell's immediate neighbors... If in any of that cell's immediate neighbors, it's not possible to place a compatible tile, then the original tile may not be placed in that cell. Yeah, that's a bit of a confusing way to word that, but that's basically saying that if I have a grid here, and let's look at this one here, right? Right, for a given cell and tile, so we have maybe whatever in there. If in any of that cell's immediate neighbors, it's not possible to place a compatible tile, then the original tile may not be placed here. Right, so that's basically saying, like, I can't place a tile here unless the tiles here overlap with this one or are compatible with it. Right, so as we kind of like collapse things down, the ones that remain here in the stack must be compatible with this one that we picked. Or all the sets of this one must be compatible with all the other ones in here, like somehow, by the adjacency rules. Not somehow, by the adjacency rules. Okay, I think we got this. So as an example, let's say the adjacency rules are like this. 2 may appear to the right of 1. 2 may appear below 1. 2 may appear to the right of 1. Or 3 may appear to the right of 2, so on and so forth. For completeness, assume that each rule above has a corresponding rule in the opposite direction. Okay, so the first would be 1 may appear to the left of 2. Suppose the possibilities of cells are represented by the numbers in the corresponding cells of this table, and we just locked in 1 in the top left corner. That was nice. Little diagram. Propagating the effects to the immediate neighbors. Alright, so if we pick 1, that means that... Right, 2 may appear to the left of 1. So 2 is allowed. 2 may appear above 1. Or, sorry, 1 may appear below... Or 1 may appear above 2. So that one's allowed. And 3... 1 may appear above 3, so 3 is allowed. And 4 is allowed there. Oh, and then 3 can also appear, so 1 may appear left of 3, so there we go. Alright, so those rules all match up, so that's how we propagate those out. But we're not done yet. For example, what can we say about this middle cell? Can the middle cell contain a 4? It's possible for a 2 to be in the cell to its left. It's not possible for a 1 to be in the cell above it. What was that? Wait, not possible for one cell to be above it. There isn't a possible one above it, though. At least not in this example. Alright, 2 may appear to the left of 4. Alright, so that's fine. 1 may appear above 4. There isn't 1 there. So we can't have the 4 there. Okay, so it isn't there. Oh, so they mean it's not possible for a 1 to be in the cell above it because of the propagation. So that's just a bit of funky wording. 4 can't be here because 1 isn't a possible choice, in other words. Because of that I guess because of that contrapositive statement, yeah. The propagation continues in this fashion until no further possibilities can be removed. So I guess we propagate from this cell, and then we keep going out. Okay. Interesting. I think we're going to need some kind of function for telling us if we can split out from here. So I should pay attention to my build errors. I got to post positive position again. I put it back in that way. After I complained about it, silly me. No, actually I don't. Okay. Alright, never mind. Getting distracted. So yeah, we're going to need like some kind of function to kind of tell us to keep going. And when we could be done propagating. So tile enablers. For a given tile cell combination, we'll say that the possibility of another tile in an adjacent cell enables the first tile to appear in the first cell. If the adjacency of these two tiles would be allowed by the adjacency rules. We'll say that a potential tile in a cell is enabled in a direction if the immediate neighbor cell in that direction permits at least one tile, which enables the first. Note that a tile cell may have multiple enablers in a given direction. In the example above, the potential 3 in the middle cell is enabled in the left direction by the potential 2 and the potential 3 in the cell to its left. A tile may not be placed in a cell if it has 0 enablers in any direction. That is, it needs at least one enabler in every direction to be a candidate tile for the cell. The potential 4 in the middle cell was not enabled by any potential cells in the cell above it. Yeah, okay, I see. Yeah. Okay, so we need some kind of enabler type. That's cool. I think we can do that. So I'm going to type to represent enabling, and then for each of the different directions in a cell, we get the lists of enablers for that cell. For a given tile cell combination. Say that a potential tile in a cell is enabled in a direction, right? And it may have multiple enablers in a given direction, right? In the example above, tile may not be placed in a cell if it has 0 enablers in any direction. That is, it needs at least one enabler in every direction to be a candidate tile for the cell. Okay, in order to be a candidate tile, okay. So the potential 4 in the middle cell was not enabled. Okay, so this is... Right, so we need to pick out the enables so that we know which tiles patterns we can remove from the possibilities of that in that cell. We generate it from this list of enablers, and I guess we go... I was going to explain cascading in the next step. So let's not peek ahead on that just yet. Let's implement this. Okay, so enablers, enabling. Going to be a large file, isn't it? go after here, say, data, enable, I don't think it's going to be a new type. Enabled is going to have basically a tuple of, it's going to be a cell and a pattern, right? So, which means we're going to need an A there. And a direction. Oh, it's enabled in a direction. So a potential tile in a cell is enabled in a direction. Okay. So we're going to give it by the pattern index, though. Pattern index and direction. That's what we're gonna do. Okay. I think we can actually use some of these as our test examples. This example is like our test for this to see if we implement it properly. So it's enabled in a direction if the immediate neighbor in that cell permits at least one tile, which enables the first. Note that a tile cell may have multiple enablers in a given direction. In the example above, the potential 3 in the middle cell is enabled in the left direction by the potential 2, and the potential 3 in the cell 2. So a tile may not be placed in a cell if it has 0 enablers in any direction. So we have a function that goes through the directions and generates these enabled structures, these enabled types, for each pattern in this current cell. All right, so we'll check 1 in up, right, down, left, and generate the enabled for each of those. I'll do the same for 2 and for 3. Alright, so we're going to need the grid. It's going to be in the grid, so this will be in our state thing. Get enabled. At. So we'll use kind of like what we do cell at, collapse at. Use the the index into the grid. And that will be a state, wave state, and it would return a list of enabled elements. Could be a list. We know it's going to be bi-direction. It could be a map too. Yeah, enabled. Let's do it like that. All right. What did I call the argument before? Just so I'm consistent here. Cell X. Okay. So the cell index. Okay, so in order to do that, we're going to have to get the cell at that location. That returns a maybe. Yeah. Leave a little note for myself again. Probably want to have an arrow T on him. I feel like we're going to be doing this a lot. And arrow T would make this a little bit nicer, so we're not... Because Haskell has, like... Doesn't... Like, it has exceptions, okay? Error throws an exception. The exceptions in Haskell are thrown in I/O. The I/O monad itself, the base, kind of like the base monad of like every program. They're the kind of crappiest error you can get, basically, because they just panic. It's like a panic. It just panics, throws, gives you some kind of error message. And error is like a function that lets you do that from anywhere in a program, in a Haskell program. And so it's no bueno in a pure function like this. But because Haskell is a practical language, it allows it. Right. And this is like deep voodoo magic that will halt the program wherever it is and throw the error there. Right. There are other functions in I/O that can do this as well. Like when you go to read a file that isn't there in the operating system, or like various other things that can happen when you're interacting with an operating system. And there's facilities for handling those. But as for like user level exceptions, when you want to define your own and handle them in kind of like a way that most programs in other languages might be used to, where they have exception handling kind of built into the language runtime, in Haskell we kind of like have ways of handling that on our own. It's not explicitly needed to be baked in so much. So that's a long way of saying that, yeah, we might want to add an error T to our stack here, not just in pure state, but add error T in there somewhere so that we can throw here without throwing into these errors. So that we have the potential for catching them and doing stuff with them that we might want to do. I'm going to leave that to a later refactoring of this. For now, sorry future me. We'll keep going because we're running a little low on time. We've got to end the stream soon. So in the case that we have the cell, we got to do something with it. We got to do something with each direction. Well, we got to do something for each of the patterns, the cell patterns. We want to collect whatever that is into a list. Okay. For each direction. So we could do a list hold L prime. I'll collect them together, and the empty list will be our accumulator over the cell possibilities. We might be able to use the generic foldable fold L to go over the array, if that's an array. It is an array, cell possibilities. We're not list specifically, but fold L. Hellos. Let me just check the data array instance for that. It's foldable. So that should be fine. documentation up just in case I need it again. Okay. Then we'll add pure. Bell at. What did I do? I need to give the grid. That's what it's telling me. Gets the wave state grid. What comes next? Grid. There we go. Okay, so whatever this function is going to be list of enabled to bool, list of enabled. I'm going to call it get enabled. Sorry, what's that list of enabled to something to list of enabled? I forgot already because my fish brain is kicking in. What we can ask you is to see where she. Bool. Oh yeah. So the Boolean here is whether this pattern is enabled. Or this pattern is allowed, is active in the remaining possibilities. So we don't want just the Boolean, we want actually the pattern indexes. It's not array dot values, it's array dot indices. So the indices of cell possibilities are the pattern indices. And we'll try to represent the patterns. Okay. That's better. So this will be enabled pattern index to list of enabled. Super duper. Okay. There's accumulated enabled. And our pattern index. Okay, so now for this pattern index, and we need to go through the cells at each direction. And we need to do something, we need to check if they're, we need to generate an enabled for each of those directions for the patterns in that cell, in that direction. All right. And so if I'm here, I gotta go up here, I gotta go right, I gotta go down. But in this particular step here, at each cell, I'm gonna go through each of those, check if they're enabled. If they are, then I generate an enabled, and I add it to here. Or I add it to my accumulator. So this is going to be another fold. Some function list. Be ACK enabled. And over our accumulator, and we're going to. Oh. Over each direction. We're gonna need this to be a stateful fold because we're gonna have to pass the grid through. I think we'll just pass the grid through. I think that's all we need, really. Grid. Yeah. Okay, now we're gonna have to go for each of the pattern indexes. This pattern index here, we're gonna have to go. Right, for here, we're saying for each of the cell possibilities, so the current cell at this particular location, we're going to get the enabled values by iterating over each direction. In that direction going to that, we're going to have to get the cell at that place and check out all that stuff. Okay, so we're going to have to hold over each of the directions. Direction. We could make this foldable, I think, by making it an enum. I think we can do that. Grab arrow. And info enum. No. We get the successor input getter. Yeah, let's not be too clever here. Like, we just make the list explicit here. That's fine. Up, right, down, left. Okay, so we need a function here. Check enabled. Check enable is going to need the grid. It's going to need the list. We need the accumulator. It's going to get the pattern, no, the direction of the pattern index and the direction. Return a list of enabled. I'm gonna leave it undefined here just to make sure I can get the types to line up. I'm going to move pattern index over here. Pattern index. Pass it in. Okay, so that lines up. So if we go check enabled, we have the grid, we have the pattern index, we have our accumulated enabled, and we have a direction. What do we do for up? Yeah, we do it that way. Right. Down. And left, like that. Okay. So in the case of up, we got to go our cell X. We have to get cell at something there. Should we treat this as a toroid? Take, in other words, take modulo our maximum index so that we don't go out of bounds. In that case, we need to know the size of the grid. We do. Grid has a width and a height. But maybe cell at takes care of that for us. Ah, it doesn't. Okay. Yes, we are going to have to... We are going to have to pause here because I'm running out of time for the stream. So I'm going to just see what we got. Okay, I'm going to stash this. Adding enabled. What I'll call it. Cool. I'm going to push up the code we have so far. Super duper. All right, and then we're gonna end it there for now, and then we'll finish this part next. We're gonna keep working on propagation next week. Get further into it. So, what did we learn a little bit about tonight? Well, we learned a bit about heaps and this kind of neat little hack to keep our choice of lowest possible entropy using a little bit of randomness. Another thing to note too is that when you're trying to learn an algorithm from another implementation like this, where there's a possibility you could just kind of sneak ahead and look at how it's done and just kind of translate it into your own language. Really make sure that it's like sinking in there. One trick I like to use is to write it in a note, write down in your own words the algorithm. Write it out in your own little notebook. So I keep notebooks for pretty much everything. And then like I write out everything as much as I can in them, so that it really solidifies in my head how it works. Because when you can kind of explain it to somebody else, you really kind of internalized it. So even though you're like kind of looking off of somebody else, you're not necessarily just blindly typing in their implementation into your language and things like that, but you're learning something by doing it as well, by kind of like reformulating things and kind of really digging in there so that you could explain it to somebody else and go, oh, and see kind of the inside of like how it works. So a little extra tip there. And then, yeah, we're learning about propagation and stuff like that. So it's an interesting way of doing it. There are other kind of like standard ways of doing what's called forward arc constraint propagation. That might work with this. And there are kind of somewhat standard algorithms for this, because it can, as you can imagine, with a really large, like a large set of constraints and a large problem space, it can be a problem that you might need to optimize for. Arc consistency is kind of like the look-ahead version of this, and there's like different levels of it. And this is kind of like a, I guess like a pseudo algorithm or pseudo code kind of explanation of the algorithm for arc consistency. And that's essentially what wave function collapse is doing, right? We're selecting an arbitrary element using our observations. We remove it from a variable, and then we propagate out all the changes until the domain is empty and we've like finished the problem. Of course, in this procedure, they return null for no consistent value. That's a contradiction, blah, blah, blah. But there's also a good explanation of constraint solving in practical artificial intelligence, I think it was. I can't remember the name, the exact book. Maybe it was Pape. Artificial intelligence programming. It might be Pape or another one. I'll try and get it for next week. But there's a really good textbook with just a lot of different algorithms in it, and one of them is this sort of constraint propagation solving, and the different approaches you can take to it. So, anyways, that's like extra reading if you're interested in this kind of stuff and you want to learn more about it and all that stuff. So, anywho, thank you for tuning in and watching. It's been a pleasure. As always, I do these streams once a week on Tuesdays at 10 after 8 in the Eastern Standard Time Zone. Next week, I will be off. I'm going to be traveling, so I won't be here. But I'll be back the week after that. And you can find me, of course, on... Well, you can find all the code for this project and others that we've worked on in the stream on my GitHub. It's github.com/Agent Ultra. That's me, Agent Ultra. And this one is wave function collapse. So all the code that we've been working on, you can find here. Paste that in the chat for you. Bang, 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 bang. And you can find me on the Fediverse on Mastodon. I am on the types.pl server at Agent Ultra there. It also has links to my YouTube channel, where you can find past streams, or if you're watching in a different time zone, you can't always watch these. You can go there and catch up on them. Always, and my website and everything like that. What else? Yeah, so if you do want to be notified of when I go online and do streams, because sometimes I do them off schedule once in a while, you know, set up your notifications, give us a follow here on the stream on Twitch, or if you're on YouTube, you can you like and subscribe there, do all that stuff. And yeah, thanks again for watching. I'm Agent Ultra. It's been a pleasure. May your monads always be free and your types always check. I'll see you next time.